Let's have a look at 6 and 7. 6. A. Again, you can try the B if you like later. Predict the enthalpy of vaporization of benzene from its normal boiling point, 80.1 Celsius. Key word here, folks, is predict, because there doesn't seem to be a whole lot of information here. And the thing about that, when you notice it, is, well, it's a textbook and there's a lot of information at the back of the book. So is that where they want me to go with this? What if I were to actually have this on an exam? How would I handle it? Well, let's just write down what we have and think about it. We want to predict. We have benzene. Sorry, my email and text traffic apparently is very busy at the moment. I apologize for the buzzing. Benzene, they told us that the temperature of the normal boiling point, normal means at 1 atmosphere pressure, right? 80.1 degrees Celsius. Great. And want us to predict delta H, vaporization. What does it equal? Okay. That's all I have. So, just going to really emphasize this. Predict. So when they ask you to predict, sometimes they'll ask you to make an estimate. We usually reserve that word estimate when we are probably going to get something from a graph or a set of data and we're extrapolating. So, but when you see something like this and it says to predict, what they're really referring you to is Troughton's rule. So you'll want to go back to the text or whatever resource you're using. Have a look at this. It's kind of neat, actually. And in terms of a formula or statement, this rule describes struggling with the focus. It's driving me crazy, and I know it's driving you crazy. Sorry about that. Delta S is about equal to, that's what my wavy line is, 85 joule per K mole. And that statement is, well, it looks like an estimate, right? That's an estimate of the molar entropy change on vaporization for, you'll see some resources say that for organic liquids, but what they're really describing is liquids where you don't have hydrogen bonding. So if you think about it for a moment, these are going to be liquids that are, not so polar, and certainly organic liquids are going to fall into that description under that umbrella. And that's why you typically see this estimate being made or prediction being made in your organic chemistry class in that lab. So yeah, these are for liquids that don't have hydrogen bonding, and benzene obviously doesn't. And we know that delta S is equal to the heat of that transition, vaporization, over the temperature of that vaporization, which of course is the boiling point. And can I just point out here, maybe backstep a wee bit, because I just landed on that formula, but this is still starting from the ds being equal to the dq reversible over temperature, because I'm working at a constant temperature and pressure. Therefore, dq reversible is actually dq sub p, and it's a constant temperature. And dq sub p is actually dH, and the temperature is actually the boiling point. So when I integrate both sides, I of course get a change, delta S, being equal to, that's actually 1 over T integral dH, because the temperature is constant, excuse me, and that then is equal to the delta H over T. And that's my formula for delta S for a phase transition. Okay? And of course, vaporization is my phase transition here. So let's come down here again and fit in the unknown. So I'm asking to predict delta H vaporization. So this is estimated to be, it'll be this times this. So the delta S multiplied by the temperature, and of course this is of vaporization, and this is my normal boiling point. So what is it? It is about equal to delta S, which we just said is 85. Not too many significant figures on a predicted number or an estimate. That makes sense. So just 2. And it is joule per K mole. It's per mole here because this is just in general. I don't have an amount of benzene that I'm describing. And clearly the temperature has to be in Kelvin. So I have 80.1 plus 273.15 Kelvin. So slip that in the calculator and I will have an answer in joules per mole. Okay, so first of all, 80.1 plus 273.15. Keep that in the calculator, multiply by 85, and I'll just write out all the numbers here and then trim it back. So 30026.25 joules per mole. So my estimate should be to 2 sig figs. So why don't I write it in kilojoules? And that'll be 30 with a decimal place. Kilojoules per mole. You can also use scientific notation. In fact, you probably should. 3.0 times. Now I could say times 10 to the 3 kilojoules per mole. Or I'll back up a minute, it's 30 kilojoules, so 3.0 time, you know what I mean. Joules per mole. Getting tongue-tied. Okay, so that's our estimate for Troughton's rule, and we can go ahead to number 7, but this one's kind of long, so I'm going to stop it here and put the next one 7 on its own video.